Hello everyone, thank you for coming. I'm Vlad Ureche. I work on the Miniboxing project. So I've come here to present something that's about generics. So I guess you all wrote a class with a generic type parameter. So when you run it past Java C or Scala C, what you get actually in the bytecode is a class C with a field object. So what does this mean? Well, first of all, it's a process called erasure that basically transforms the type parameter to its upper bound. But what is interesting is that this requires boxed primitives. For example, you probably know Java lang integer, right? This is the equivalent of int. In Scala, you don't see that. You have Scala int, and Scala C does the heavy lifting for you. It converts from one representation to the other, does all the work. But actually, you still notice something. You notice it on the performance side. On the performance, you will see that heap objects get allocated. So you have time spent for allocation, then time extra GC cycles. And of course, indirect reads, because you access a value through a pointer, and broken locality. So these are problems that matter a lot. What do we do right now in Scala C? Well, you just add a specialized annotation there. And with this specialized annotation, what it does is magically transforms the class such that it will have good performance for primitive types. Now, what I'm going to try to convince you today is let's use @miniboxed instead of specialization. Let's see why. So what is miniboxing? Well, when you put a miniboxed annotation, it's pretty much like a specialized annotation. But we took out the limitations that we knew in specialization, and we generate less bytecode. Okay, why does it matter? Well, this opens up the opportunity to actually specialize Scala collections. So everybody's complaining that Scala collections are slow. Indeed, they sometimes are pretty slow, so we should do something about it. Okay, so first of all, specialized. We've seen, one thing that I want to ask everybody, please ask questions right away. So if I lose you on the road, please ask me. The presentation shouldn't take more than 40 minutes, so we're okay with interrupting and asking. Okay, so you have class C, marked with specialized. What does it happen? We start from a class C, and specialization, as the class gets compiled, automatically creates specialized variants. What does it mean? It's a copy of the class that inherits from the generic one, and it's adapted for a primitive type. Okay, so if you create a new C of int, what happens behind the scenes, the code gets rewritten to new C $MCISP, which is the equivalent of C, just that it's adapted for integers. Okay, so this being adapted to integers, it means the field that you see up there in T of type T, it's actually a different field of type integer. Okay, so far so good. If you do a C of ABC, string is not a primitive type, it will just create a normal class. Okay, so far so good. There's a similar transformation for methods. When you have methods, what will happen is that you have different copies of the methods, each of them having the body adapted for the primitive type. So you can get speedups of 20, for some cases you can even get speedups of 20x just by adding this annotation. Okay, that's very good. So why do we want something new? Well, there are some limitations to it. And I'm going to talk about two of them that we address in Miniboxing. Duplicate fields and broken inheritance. So duplicate fields, let's go again to the example of C with the specialized annotation. So if we have a single class, we have these subclasses basically, which are specialized. Now, when we create a new class of ABC, it gets a string. So there, it must put the value ABC into a field. In that case, the field is T, and it's a field of type object. Well, let's now create a C of int. and it creates the specialized variant. And guess what? It puts it in a different field, named differently because you don't have a field overriding on the JVM level, on the bytecode level. And I'll let you look at it and tell me what exactly is wrong with this. Can you tell me? Exactly. So we have two fields in the specialized variant. One is the generic one, which is inherited, and one is the specialized one, which is defined in the class. Okay, so that's not really good. We have this bug, long-standing bug, and it's been there for a while. We haven't fixed it just because it fundamentally changes the transformation. Again, let's go to limitations and take another class, D. Again, specialized, which extends the previous C. Okay, so we have C and D when we start compiling. Then specialization adds the specialized classes for C. And let's assume in C we define now a method foo. Well, we'll get a specialized version of this method foo is in the specialized version of the code, of course. And now let's say we create D, the specialized variants of D. And one of them wants to call the specialized variant. Well, what would be ideal here is that the specialized variants of D would inherit from the specialized variants of C. Pretty obvious, right? I mean, that's what you would expect. Well, it's not possible because on the JVM you have single inheritance. So if you already inherit from D, you cannot inherit from C $MCXSP. Okay, so this is another bug that's not possible to address directly. Now let's see how Miniboxing does this. Well, first of all, again, we start with the class C, but look carefully at C. It actually transforms into an interface. So when we do this little change, actually we get a single field, T. And we get specialized getters and setters in the interface. This makes it much easier. Now we fixed the duplicate fields. What about the next problem? The broken inheritance. So again, we have C with the two variants, and we just add D. Interfaces extend each other, classes extend each other, classes implement interface. All okay? Fixed. But maybe you're wondering, so for specialization I showed you many classes. There were a lot of classes there. Now for Miniboxing I just showed you two variants. We're getting to the next problem, which is bytecode bloat. Let's take this example. Function2 is very common in the library. You don't see it. It's when you write two arguments in parentheses, results in something. You usually use it, for example, in folding. And it has three type parameters. Obviously, two arguments and a return type. Well, each of these should be specialized if you want to do full specialization on 8 Java primitive types, plus unit, which is a Scala primitive type, plus object, because we also want to carry objects. Now, can you tell me how many traits this will produce? 1,000, exactly. 10 to the power of 3 for the 3 type parameters. Of course, this is upfront bytecode that we generate not on demand, but right away put it in your jar file. So you can ask me later why we do so, but this is the way it's done currently, and it's probably here to stay. So this is too much bytecode for the Scala library. 1,000 times, well, we still want to distribute it via Maven and not via torrents. So we need to stay with something small. So we can do better. We need to do better. Not that we can, but we need to do better. So one day in 2012, Miguel Garcia, the author of the new backend for Scala, hopefully the optimizer will be merged soon and you'll get a new cool backend. He walked into my office, he knew I was working on specialization, trying to address this problem of bytecode, and he tells me, look, from a low-level perspective, you only get values and pointers. These are the two cases. And indeed, this is the case because pointers are not accessible on the JVM level. So we cannot, since the GC should be able to rewrite them, copy them to different locations, we're not allowed to touch them directly. Therefore, we have to make this compromise of having pointers and value types. And I was trying to figure out, hey, what exactly can I make of this? And I was looking at the value types. I was staring at them. What can I do? I mean, sure, it's value types, but actually then I figured out, well, everything can fit on a long integer, whether it's an integer, whether it's a float, whether it's a short. You could just encode it on a long integer. And then the miniboxing idea was born. So basically it starts from a tagged union. If you used or coded virtual machines for a dynamic language, you probably wanted to have this. It's basically a tag which stores the original type and a data, a payload, where you can put different types of data. Well, with this, basically, I can encode everything, right? I can encode a Boolean, I can encode an integer, I can encode a float. There's no limit to what I can encode in that. So this is somewhat similar to a boxed object, right? Because a boxed object has a header, like the tag, and the data, where it keeps the value. Well, not really, because this is not on the heap memory. So we don't allocate a new object on the heap memory. We don't need to garbage collect it. Furthermore, it provides us with direct access to this value, which means not that we need to access a pointer, but we can read it right away. So we reap the benefits of unboxed values through this. Now, we can with this, we can reduce the number of variants. So you have one variant for values with this encoding and one for objects. Therefore, just two of them. And this is exactly what Miguel was saying. From a low-level perspective, there are only values and pointers. We have one for values and one for pointers. So let's take an example. Choice is a method, a simple method, is generic, and it basically takes two type parameter and two values. And it makes a choice between either the first or the second argument. In this case, I made it random, so it will pick whatever, one of them. And now let's say we annotate this with miniboxed, and let's say we want to translate and basically get the variant that is specialized, the one that handles value primitives. So this is usually called choice J, or at least this is the way it's called right now in the implementation. And let's try to figure out what would be its signature. Well, very, very naive tagged union would have a tuple with tag value, tag value, tag value. What's wrong with this? Sorry? Oh, yes, that's very important. These are objects. And furthermore, if you look at it, we get the tag twice. Not necessary, because we know the two values have the same tag. And what's even worse, we return it to the caller who gave us the tag, right? So there should be really no reason to pass it back. So we're in a statically typed language, right, in Scala. Why not use that? We can basically open the tagged union, split apart the tag, split apart the value, and have the value go up basically corresponding to the type parameter. This is somewhat similar to a reified type, like if you have a class tag, for example. So, of course, the values are encoded as long, as I said before. So the result is this. This is the specialized variant. And if you look carefully, the tag is actually a byte. It's not a class tag, it's not something very expensive. It's just a simple tag which will tell us which of the primitive types we encoded originally. Okay, so let's go back to the bytecode. Function2, yes?
But coming back to the previous example, why do you need this tag at all? Now with t in advance statically, you can just have used the corresponding match in the...
Very good question. So the question was, why do we still need the tag? It's not used anywhere in the code right now. The answer is, first of all, you might need it depending on the body of the method. We'll have an example later. And the other answer is, you might be overriding with in the future, you might be overriding this method. And the overrider method might need the tag. So you're not allowed to take it out as an optimization. But theoretically, if you knew the method is final and it's not using it in the body, you could take it out. Okay, so going back to function2, we have 3 type parameters. With specialization, we said it's 1000 traits. With miniboxing, it's only 8. So 100 times less bytecode. So we expect it will be usable on the library. Now, before we wrap this explanation up, let's go into some internals. So before the benchmarks, let's see some internals of how we do this transformation. You have the insights used for the transformation itself. Well, this is where it gets complicated. Time for the hard hats. So let's say we have a programmer that fears the number 13. So some superstitious programmer. And he says, well, choice, I'd rather not pick number 13. And how do I figure it's generic, so it might not be number 13? But he says, well, if the hash code is 13, maybe it's 13. So the question is, okay, we can translate it to choice underscore j, no problem. We know the arguments, we know the return type. But how do we translate t1.hashcode? Well, t1.hashcode, well, we know t1 is miniboxed, so it uses a representation, but we can't call it on a long, because you have all kinds of surprises in the hash codes. For example, here, true and false have pretty random hash codes on the JVM I'm using. So you cannot just rely on some encoding. Well, what you need to do is basically introduce a conversion. So it's minibox to box in this case. Basically takes the miniboxed representation and boxes the value into a type t. And then it takes the type tags. There's your answer to the question. The type tag is necessary for the hash code. Okay, so we have conversions from minibox to box, from box to minibox. And then we can, in order to get the hash code, you first box the value back and execute the hash code method. Of course, this is not naive. The way it's implemented right now is optimized, something like an extension method. But let's not go into that. This is the principle. We need to convert and run the hash code. And performance-wise, this is still okay because we have several types of conversions. We have conversions between miniboxed and unboxed integer types, which are free on the x64. So basically, there's no overhead, very little overhead. There is an overhead, however, between miniboxed and floating point types. It's not free. But Rex Kerr, he suggested a different translation, which I implemented, and it works much better. So if you're interested, you can try that out. Between miniboxed and boxed values, that's what we're trying to avoid. So this is where it's at the interface between generics on one side and miniboxed on the other side. What do you do in this case? Take whatever is generic, put a minibox annotation on it, and it will run better. We'll have an example. Okay, so let's go to an example. This will be the last example before the benchmarks. So let's take a list, a method list, which takes 2 arguments and creates a list out of them. It's a pretty simple method. And if we actually look at the implementation, what Scala C will do is it will desugar this into an apply. Well, this apply, we'll put it in, and let's try to transform it. We know the arguments. We know exactly how we transform the arguments. We put a type tag, we put two longs, these are the two arguments, but what is the return type? Well, the question is, how exactly do we transform list of t? Any insights? Could we make it a list of long, maybe? Anybody who says it's a list of long? No. Okay, thank you very much. So, list of t. How do we transform it? Where for specialization it's pretty simple, right? T becomes int, therefore list of t becomes list of int. For miniboxing, it's still list of t. So how do we get a specialized variant for list of t? Well, if you recall, we have list of t and we keep the type parameters around. So we just have list j and list l. And the implementation will be the one specialized. But we don't specialize deeply inside generics. So with this, we know it's returning a list of t. Can you look at this example and tell me if you see something that's wrong in here? Exactly. So these two, they're long, and actually the expected type is a t. What we need to do is add some conversions. In there, add the conversions, and then it's all right. It works. Now, of course, you don't like this because we're boxing. Of course, we're going back to the disadvantages of generics. So what you could do is take take the list, go to its object, add the apply method, and mark it as miniboxed. And what you will get is the bottom translation, which will just apply the method apply j, and there's no boxing involved. Okay, so we've seen that the transformation here, but it turns out there's more to this. It's a bit more complex than this, but it's also a very nice general mechanism for doing transformations. And Eugene gave it a shot 3 months ago. He was interested, and in a week he implemented the value class plugin with support for multi-param value classes. In a week. It's here, we have the documentation, we can try it out. But I won't go into the theory of this. You can ask me later, because it's a pretty complex example. It's a pretty complex talk. So let's go to the benchmarks and see exactly where we stand with miniboxing. We have an implementation that's pretty stable. So we tried it on a mock-up of the Scala linked list, so a mock-up of the Scala collections library. This is joint work with Aymeric Genet, and we wrote basically a mock-up of all the things necessary to do a simple benchmark. That included Function1, Function2, Tuple, and pretty much all the things you hate about the library because they're complex. They're there. The benchmark was least squares method. So it's basically taking a set of points and trying to fit a straight line through them the best way possible. And you can see here the results. Considering an infinite heap, meaning that there's no garbage collection happening, we are 1.7x faster than the Scala library. And then if you consider garbage collection, because then you start seeing the fact that miniboxing actually has a more optimal representation, we get 2x faster. Unfortunately, I don't have the numbers for specialization on the slide because I have no idea why. After 1.5 million elements, it started consuming a lot of memory and continuously running into GC cycles. Okay, but we said we're interested in bytecode, right? Because the bytecode was the #1 priority. So let's see the bytecode, how it looks. Generic, minibox is 6 times more. Remember, we specialized the function 2, so that's a lot of bytecode. And then specialized is about 100 times more than generic. So I guess you could live with a bit larger library to reap the benefits of not boxing, but not 100 times more. Okay, so again with Miniboxing, this time on the Spire library. There are plenty of benchmarks there. Here's a benchmark called Complex Benchmark, and it has two versions, Complex Direct and Complex is Generic. I call them in this slide best case and worst case because it's simpler. And you can see Miniboxing, of course, since it has additional transformations, its peak performance is not as good as Specialization. But this is somewhat expected, right? On the other hand, the worst case in this situation is not as bad as Specialization. So there's a trade-off somewhere. There are also benchmarks on which we do not that good. So for example, one is Rex Bench, where Miniboxing is twice as slow as Specialization. Still, it's 3 times faster than generic, so we're okay. But I guess the takeaway message from specializing Spire is that if you really need maximum numeric performance, you better stick with Specialization. If not, if you just have a project and want to lightly take off some of the cycles from using primitive types, you might be interested in generics, in Miniboxing, sorry. Okay, so benchmarks on the bytecode, it's pretty good, it looks pretty good. Miniboxing adds a 50% increase. Of course, Specialization does more than that, but have in mind the fact that Spire is hand-tuned for Specialization, meaning that it knows exactly those primitives for which to specialize such that it makes sense. Therefore, it does not create the 10 variants possible. It just creates those that are needed. So with this in mind, we still beat pretty much, we generate half the code of Specialized. Okay, so I need to thank a lot of people who helped out with the project, who developed. I won't name them, but they're on the website. So once again, Miniboxed is specialized, minus the limitations of Specialization, minus the code bloat. And we're really looking forward to trying it on Scala collections. Now, since I probably finished much earlier than is needed, I'm welcoming any questions you may have. Unfortunately, I won't be able to do a demo because my computer doesn't want to project. But you can come here and I'll show you. Thank you.
Is there a possibility to merge it to the Scala master, or it's just academic work?
Well, at this point, it's quite stable. So from my side, I'd be interested in trying it out. The problem is, right now, it doesn't cover exactly the same use cases as Specialization, which is super high performance number operations. So what would need to be done is to somehow either put Miniboxing inside Specialization or Specialization inside Miniboxing. And it's not very hard, but there are some tricky corner cases that need to be considered. So I think it's still something that needs to be done. Right now, I would be very happy to see users trying it out, seeing what are the corner cases, and as soon as it works stably better than Specialization, we already see some cases where it's better, some cases where it's worse, then we can think about, let's take it to the next step to the Scala trunk.
Can you go back to the signature of Function2, please?
Oh. Plenty of slides. Okay.
Okay, so there is a not that well-known limitation of Specialization that if you specialize in for multiple arguments and some of the argument in the location of instantiation is generic, then you won't even get specialization for the arguments that still are. So for example, if you have function2 specialized in this case for all arguments in the result type, and if one of the arguments is in this particular case not known in the location site, it's an object, then specialization won't kick in. What's the case with Miniboxing?
Okay, so let me maybe repeat the question. So one of the limitations in specialization is, despite having a specialized variant of the code available, if your call site is generic and you know nothing about that type parameter, it's not specialized, there's nothing done to it, it's not going to use an optimized version. And that's true. It's exactly the same problem with Miniboxing. And the underlying problem is that in Scala, we don't carry reified types. Like, for example, the .NET Common Language Runtime carries reified types, which means there's, for every type parameter t, there is a little object that the framework carries automatically that describes type t. And therefore, on any call site, there is information about t. But as I showed you in the beginning, it's actually the case that C takes an object there. There's nothing special. It's a trick, a signature trick that you have the type T. Okay, you had a...
I have one more question. So if you'll come to the inheritance graph for Miniboxing, then for Miniboxing.
Yeah,
then
going.
Yes. So now, is it possible to configure Miniboxing to generate not 2 classes but 10 for this particular argument as specialization does, in order to be able to not pay the overhead of conversion of double to long bits and still be able to use it through the inheritance chain?
Good question. So right now, Miniboxing either does 2 versions or 3 following Rex's suggestion. So we can generate either 2 or 3. The third would be optimized for floating point, because there is actually an overhead of transforming from Minibox to the to floating point and back. But creating all the specializations would mean also we need to take out the type tags. And it's also a compatibility problem. If you have 2 classes, one having just 2 specializations, 2 variants, and one having 10, how can you bridge the gap when you call from one to the other? You would have to take, all right, what's the type tag? And let me, based on the type tag, match the correct version. Of course, this is expensive. So unfortunately, right now, I don't have a good answer to how you could have in the same file different translations. Yes? Oh.
Okay. Hi, Vlad. First, thanks for your excellent work. I'm a little confused and interested in how to basically size your storage value. I mean, from what I got is basically you say, okay, everything fits in a long. So there's some overhead, basically. So first, my question is, how much is this performance impact you have? Second is, have you thought about using different storage sizes for the values? So 4 bytes, 2 bytes. And third question in that direction is, what about value classes? Could you elaborate a little more on that? So what if I want to store a complex, for example?
Okay, so let me take them one by one. So the overhead of the storage type. There is an overhead, certainly. Unfortunately, it won't go away. But it's cheap enough that it won't affect, at least it won't affect much more than it affects to have a pointer. So if you think on a 64-bit platform, a pointer is pretty much the same length, 64 bits. This is a trade-off in the end. Of course, if you're after super high-performance numeric operations, then you will want to have the storage type and pay the bytecode cost. Then the other question was about using several storage types. This is what's happening. So if you have several storage types, the mechanism for transforming data representations still works perfectly. There is no difference in how it works. And actually, in the 3-class translation, we do exactly that. So we have storage type long, storage type double, and basically the generic one. And with this, we could also fit integer if we wanted to. So yes, it's possible. Third question, value types. So with the same, we like to call it the frog. The frog mechanism. You can also do encoding, basically take 2 floats, put them in a long, or do these kinds of transformations. Or you could even do value classes per se. I mean, you just put a class there, put the fields, and this gets inlined. So this is a very general mechanism for saying, I have this representation, and this actually translates from the high level, for example, Scala int, into int and Java lang integer, or from float to long, or to float if it needs to be boxed in some context. So this will be accommodated by the mechanism. Not exactly in the Miniboxing plugin, but you could develop something right away. I mean, 3-4 days of work. Okay, there was a question there.
If you're using some function like min, max, which takes generic or object parameters, in case of specialized, I guess it would be called the generic version of function. What would be called in your case, and how it will work in this?
So when you take a generic max or min function, and you will also need a numeric or some ordering between the two arguments. And therefore, you still need to have a type class with this ordering. Now, if this type class is specialized, what you will need to do, or miniboxed, what it will happen is that if the function to compare is miniboxed and the numeric or ordering is specialized, the specialized variant, the specialized compare method will actually be invoked. And therefore you won't have any overhead. For specialization it will use the primitive type. For miniboxing it will use whatever storage type you have there, either long, double, or whatever you want. So it's a matter of basically adding the miniboxed annotation in 2 places actually, on the ordering and the function. Yeah. If you want, I can show you later more. You don't have to do it by hand. You just, when you write the type parameter t, you add an annotation at minibox t. And then from there on, miniboxing takes care of everything, meaning it creates the second method or the specialized versions of the method and transforms the body. And also wherever it meets, it sees that min-max function with a primitive type, it will automatically transform it to use the minibox version, the optimized version. So on the website, there's a tutorial that explains exactly how this works, where you show, basically, I show what are in a trace. If you have a program trace, you will have some initializer, which is an invocation that starts to use miniboxing, and it's usually one where you have the type, the primitive type right away there. And then there are propagators, so methods which are miniboxed that themselves will call other miniboxed methods in the stack trace. And finally, you will get to one that is generic, which is the inhibitor. So throughout your stack trace, you will get, you just need to be careful to not have inhibitors in the middle of your main algorithm. and then it's going to be fine. Maybe we can take it offline and then I'll show you some examples.
One more question. What about if you have a normal value type that, for example, wraps along, and you use this value type, will you get the long version or will you get the object version with boxing?
Can you repeat? So you have a value class.
You have some kind of, I don't know, something which really is a double, but you, for type safety reasons, you have a wrap double which represents,
Okay.
I don't know, whatever, a currency or something. And then you use this thing as the type parameter for Miniboxing. Will this be use the boxing part or will this use the long storage?
Very nice question. It will use the boxed representation for the reason that when you pass it, you cannot pass a long because there's a confusion between what exactly was that originally. Was it a long or was it something else? But there are ways around it. I mean, if you have a specific application, you can design something that will add a type tag necessary for carrying the original type, and then you can put the long right away. But there's no, so far I haven't seen a general approach to do this. You'd have to have a set of constraints that you put on your code, and then have a little plugin that transforms it and makes it optimal for your use case. Okay, Dimitri?
At least in the specialized case, there are examples when if you have only part of your code specialized, because you'll be going from specialized to non-specialized versions, instead of getting the speed up, you will actually get a slowdown, because you have multiple conversions that were just in place to not do any actual operations on the unboxed versions. So in case of, and for specialization, it can take up to 20 times slowdown on several 2 examples. Have you tried to investigate the same issue in the mini-boxing?
Okay, good question. No, I'd love to see those examples. I know there's a risk when you have something in the middle of your optimized trace that boxes and unboxes later. You basically create on each invocation, you create garbage. And though we have exactly this problem with the value class plugin. So here what you have to do when you have, for example, a method that returns a value class with multiple parameters, you cannot unbox it because the JVM doesn't have multi-stack, multi-entry return. So you need to box it. And what we see is basically a huge number of small-lived, very short-lived objects that get created and thrown away as soon as the method returns. So yeah, it does break performance. I'd like to see if I can do something about it.